cover the concepts of probability distribution function, probability density function, and a few numericals related to these two concepts. Okay, let me review what we have seen in the previous classes. Okay, we are defining experiment. Any action that has got an outcome is defined as an experiment. So in this experiment, we have got deterministic experiment and random experiment. Okay. In deterministic experiment, the outcomes are predictable. The outcomes are known a priori. Okay. In random experiments, outcomes are unpredictable. I may be knowing the outcomes as head or tail, but on a given trial, what is the outcome? I do not know. That is what I mean by outcomes are unpredictable. Now, the outcomes are also referred to as events. You can combine one or two outcomes, or you can consider the outcome itself and you can label that as event. Okay. We have defined a term referred to as sample space. All the outcomes of the experiment are shown to be in sample space S. So in sample space, we have got outcomes and events. Events are nothing but redefined combinations of outcomes. Okay. Then when we are dealing with random experiments, we found that in some experiments, outcomes are numerical in nature, and in some experiments, outcomes are non-numerical in nature. So what we did in the previous class, let us represent the outcomes of the experiment where non-numerical data is coming up by numerical values. Okay, by some rule, we assign numerical values to the outcomes of the experiment. So what is the scenario now? I have the experiment, I have outcomes, I have numerical values. Okay, so the set of all these numerical values are represented by a random variable capital X. So capital X is nothing but a list of so many values. Is it okay? When I perform the experiment, I get outcomes, right? Sample space, yes, is nothing but collection of all outcomes, right? So what is the inference? For each outcome, I have one numerical value. Is it fine? For each outcome, I have one numerical value. Okay, let me compress the screen, zoom in, right? So from hereafter, what we do, whatever is the experiment, we always refer to numerical values. So I will say a random variable x is given by 1, 2, 3. What does it mean? The random variable is taking values 1, 2, 3. But what is the underlying experiment is not known. The underlying experiment can be anything. Okay. For the but it is very certain that the experiment has got 3 outcomes. For those 3 outcomes, I have given the numerical values. That much I am clear. But the underlying experiment, I am not very clear. What does it mean? I am dealing with numerical things. Whatever is the underlying experiment, the experiment can be constituting a committee, selecting a colored ball from a box, or the experiment can be selecting a resistor from a heap of different resistors, or selecting a diode from a number of diodes on the table. Okay, like that, experiment can be anything. But finally, I am dealing with only numbers because for each possible outcome, I have assigned a number, right? So also what we saw was Each outcome happens with certain probability. What is the probability of outcome 1 happening? What is the probability of outcome n occurring? If a if each outcome is represented by certain value of probability, since each outcome is represented by a numerical value, what is the probability that the random variable x takes a value of 1? It should be same as the probability of outcome 1 taking place, provided outcome 1 is mapped to numerical value 1. Likewise, what is the probability of x taking a value of n if outcome n is mapped to numerical n? By this mapping, what we said was we are mapping the outcomes on real line. All are numericals. So you can assign negative values to the outcomes, positive values as you like. Okay. Once probabilities are listed, what is that next thing we did? Now you indicate values of the random variable along x-axis. You show probabilities along y-axis. So I will show like this. What does this mean? The random variable x is taking a value of xi. What is the probability of random variable x taking a value of xi? That is indicated by a vertical line. What is the probability of random variable x taking a value of xi plus 1? The corresponding probability is here. Like this, we can have different probabilities, right? Xn. I hope the concept is clear, right? Once the probabilities are plotted like this, next concept comes. What is the probability that the random variable taking a value of x less than or equal to xi? Okay. Then what is the probability that the random variable is taking a value less than or equal to xi plus 1? So you put p of xi, then p of x less than or equal to xi plus 1. This we have defined by probability distribution function fx of xi. Here it is referred to as probability distribution function fx of xi plus 1. Is it okay? How does the probability distribution function appear for this case? When x equal to xi, consider xi slightly on lower side of xi minus. There are no events, right? So at this x equal to xi, the probability jumps. By what amount it jumps? P of xi. At x equal to xi plus 1, still there is a jump in probability. How much of jump is this? It is equal to P of xi plus 1. Like this, the distribution function keeps growing. So along y-axis, I am plotting distribution function. Okay. So let me erase this. What I wrote is correct. Only thing is I am creating space so that the things become a bit clear to you. So along y-axis, I am plotting probability distribution function. This height is P of xi. Okay. Any questions, please, till now?
No, sir.
No, thank you. So what is x-axis, please? Values taken by the random variable x. Please don't forget to put the axis, label the axis. That is very important, right? Once I have a curve with staircase approximation, staircase representation, it is like a stair, right? I have another concept referred to as density, probability density function indicated by fx of x. Probability uh, density function. Anyway, I will write down. By probability density function, what we mean is it is the derivative of the probability distribution function. By derivative, what we get? By derivative is fx. Okay. When I take the derivative of that, I get at x equal to xi, I get sudden transition. At x equal to xi plus 1, there is sudden transition, right? What is this magnitude? P of xi plus 1. What is the magnitude of this impulse at x equal to xi? It is P of xi. Is it okay? And what is happening to the distribution function between xi and xi plus 1? The distribution function is taking a constant amplitude. When the amplitude is constant, the derivative becomes 0. So in density function between xi and xi plus 1, 0 appears. So we have defined two functions now. First is random variable is defined. It is a rule by which the numericals are assigned to the outcomes of the experiment, right? So random variable is defined. Once random variable is defined, we have defined probability distribution function. The notation is fx of x. And what is the definition of fx of x? This is probability that random variable x takes a value less than or equal to x. Then later we said probability density function. Okay. By notation it is lowercase f and subscript is random variable x. How did we define this? It is derivative of the distribution function. Okay. And when you see the terms here, I have two levels. Okay. Distribution function is f. Okay. For what random variable? For random variable x, capital X. What values the random variable takes? Indicated by small x. Is it clear? Likewise, I have density function. What is the notation for a density function? F. For which random variable it is? Random variable x. What values the random variable takes? Small x. Is it fine? Or this is the argument which is plotted along x-axis. So this should be uppercase and this should be lowercase. Always please take care of that. If I have a random variable w, so how I should represent the corresponding distribution function? Something like this. The argument must be a lowercase alphabet. Okay, let me stop here. Then I will take the help of the textbook. Once the probability distribution density functions are defined like this, is there any set of properties that define the random variable? That I need to justify. They got selected. Yes. Okay. Right. Um, okay. Yes. The textbook. Let me take the help of the text. Okay. What I am trying to show is I want to refer to um, the properties of the um, distribution and density functions. Okay. By distribution function, what is that by definition? It is the probability of random variable x taking values less than or equal to a specific value. Okay. So what properties does it possess? This is the list of the properties. Okay. This is what I am referring to. Properties of distribution function. 6 properties are listed. Let me show the side heading also. Okay. It is the distribution function of x. Okay. Now you see the first property. It is fx of minus infinity. So what value the random variable is taking? The value taken by the random variable is indicated in the argument x equal to minus infinity. Normally what we do is fx of x is probability that x takes a value less than or equal to minus infinity. Minus infinity is reserved for an impossible event. Okay, that is the idea in this discussion. X equal to infinity includes all possible events. By definition, the distribution function fx of x is probability that x takes a value uh, less than or equal to minus infinity. When x is taking a value less than or equal to minus infinity, it is not including any event. So the distribution function has got a value of 0. That is how fx of minus x is 0. Then the next thing is fx of okay, fx of infinity. By definition, fx of x is probability that capital X is taking a value less than, okay, let me write down so that you will appreciate the discussion, right? On left hand side, I have the properties. Okay. So property 1, I am writing down on the right hand side. Let me use pens, tools. Fine. First property is fx of minus infinity. By this, what I mean, probability that x is taking a value less than or equal to minus infinity. Normally, what we assume is the random variable is taking values beyond minus infinity, not even minus infinity. So, x equal to infinity is an impossible event. When it is an impossible event, the probability of that is 0. So this is 0. That is how first property can be proved. When it comes to second property, what is this by definition? Probability that x takes a value less than or equal to minus infinity. So what values of x should I include? All possible values of x. X equal to say value 1 plus probability that x takes a value of say value 2 and so on. All possible values I should include. When I include all such possible values, what is the total probability of this summation? It is 1 because it is including all values of x. And in the previous class also, when I plotted the distribution function, okay, for different values of x, how did I show staircase, right? When I considered all possible values of x, the final value becomes 1. Okay, say x is taking values 1, 2, 3. If the probability of occurrence of 1 is 1/3, probability of occurrence of 2 is 1/3, probability of occurrence of 3 is also 1/3. Okay. Since distribution function is cumulative distribution function, whatever exists at that instant and before that instant should happen at that event. See, x equal to 1. So this probability is corresponding to x taking a value of 1. Then this probability refers to x taking a value of 2. But to this probability, I have added the previous probability. That's why there is step increase. Okay, at x equal to 3, the event happens with this probability. To that event probability, I need to add the step existing before that. Is it fine? So from the second property, it is clear that by fx of infinity, I mean the sum of the probabilities of all the events taking place. Then the third property says the distribution function is always bounded between 0 and 1. So the 0 value is over here and 1 value is at the top. Okay. From the figure itself, it is clear. So in other words, the distribution function always accounts for all possible events of the experiment within the constraint of x taking a value of small x. Small x is 0. So fx of x is 0. When small x includes all possible outcomes, x of x upper value is 1. The fourth property says if I consider two values of x, okay, I am considering two values of x. When I consider two different values of x, say x1, x2, and x2 is on higher side of x1, what does it mean? Now I am considering, okay, in this example only I will take. I hope your figure is okay. Okay. Now you consider x1 as 1.5, say x2 as 2.5. So apply this x1 and x2 to property 4. So from property 4, if x1 is on lower side of x2, then the value of the distribution function will be on lower side of the value of the distribution function for x2. See, where is my x1? Here is x1. Okay. Where is x2? 2.5 here. Now you see the values of the distribution function. The value of the distribution function is on higher side for higher limit. Is it okay? Then fifth property is, okay, you consider, okay, fifth property, consider the quantities on the right hand side of equality sign. On the right hand side of equality sign, I have fx of x2 minus fx of x1. That difference gives me the probability of random variable x lying between x1 to x2. Let us see from this figure. Suppose x2 is 2.5, x1 is 1.5. The value of the distribution function at x2, that is 2.5, is 2 by 3. Okay. Okay, let me draw again because the same figure is used. Let me draw now in a better way. X-axis is values taken by the random variable. Random variable is taking values, 1, 2, 3. X is taking values 1, 2, 3. I want eraser now. Okay. Uh, Next pen I have to take, right? Draw, yes, pens here. Okay. 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 This is 1, that is 3. Okay. Probability of random variable x taking a value of 1. Distribution function, let me plot. This is 1/3. Okay. This is 2/3. This is 1. At x equal to 1, this is the probability. X equal to 2, again 1/3. X equal to 3, again 1/3. Okay. Now x2 is 2.5. X1 is say 1.5. When I take the difference between the two distribution functions, values of the distribution functions at those 2 points, that is 2 by 3 minus fx of x2, it is 2 by 3, fx of x1, it is 1 by 3. I am reading from the graph. Okay. When I take the difference between the two, what is the difference? It is 1 by 3. So probability that x, random variable lying between 1.5 to 2.5, is 1 by 3. That is the meaning. Is it appreciated? Fifth property is covered. Sixth property is the distribution function value, okay, at x equal to x superscript plus is same as the distribution function value at x equal to x. X equal to x, say x equal to 1. At x equal to 1, I have shown sudden transition, right, from 0 to 1. Sorry, 1 by 3. So what sixth property says is at x equal to x superscript 1. That x superscript 1 is 1 plus delta. Delta is so small that 1 plus delta doesn't include any possible outcome of the experiment. Suppose the possible outcome of the experiment is mapped to 1.1, my delta should be less than 1.1. Okay, that is the idea of sixth state. So the value of the distribution function at exactly fx of x at exactly capital X equal to small x is same as the value of the distribution function at x equal to small x plus small increment, okay, which doesn't include any possible outcome of the experiment. Any questions, please? Normally, you may get a question like state the properties of distribution function. Justify the properties. In that case, you have to give logically the reasoning to prove these properties of distribution function. Okay. Um, okay, let me go back. Properties are being covered. Then another thing, interesting thing is, let me consider this distribution function where there are step increases. So this distribution function is referred to as staircase waveform. Okay. What is important in this staircase waveform is I have different values for x1 and corresponding probabilities. So I am plotting the distribution function fx of x at x equal to x1, x2, x3. Okay. How do I show? Like this staircase waveform I am showing. This is a typical case, right? It doesn't mean that every distribution function should have staircase wave. If there are some staircases like this, how can I consider this distribution function? This distribution function can be viewed as having a unit step function at x equal to x1. What is the value of, what is this magnitude? Step height, it is equal to probability of random variable x taking a value of x1. In a simplified way, we say probability of x1. Okay. There is one more unit step function at what value of x at x equal to x2. What value does this unit step, step function take? It is given by p of x2, where that step function is happening at x equal to x2. Like this, at every possible value of x, I can show step functions at x equal to x3, another step function. The magnitude of that is the value of random variable x equal to small x3. How do I get this original staircase waveform? By adding the step functions in figure A, figure B, figure C, and so on. Is it clear? So, two things we should remember. What is the magnitude associated with the unit step function? It is p of x1, where that step function is happening at x equal to x1. In figure B, what is the magnitude of the step function p of x2 and where it is happening at x equal to x2? Is it okay? In figure C, the magnitude of the step function is p of x3. The step function is happening at x equal to x3. Now, to get the distribution function fx of x, I need to add up all these step functions. How do we show step function? U of x minus x1. How many such step functions? N such step functions. So I need to add up all these step functions to get the given distribution function. So that is nothing but summation over all these products x minus xi, where I is running from 1 to n. Is it clear? That is what is written in this figure expression. Okay, let me again expand this. Yes. So the distribution function fx of x equal to summation over the product of p of x equal to xi, u of x minus xi. So u of x minus xi is unit step function. It is scaled by p of x equal to xi, which is nothing but p of xi times, that is simplified as next page, I think, right? Okay. It is simplified as p of xi. This already I have indicated. Okay. And any questions till now, please? This is the example being given in the textbook. I hope the figure is clear. Numericals are visible. So what is this function? It is distribution function. What inferences can we get from this distribution function, please? Can you please speak out? Unmute yourself and speak.
It has the staircase representation.
Uh, okay, staircase. Very nice. Any other inference? So please speak. See, when you speak, you are allowing yourself to express. When you express, it doesn't mean, it doesn't bother even if you are wrong. Response is more important than accuracy of the answer. I will be happy if you respond. What information do we get from this graph?
We
What
can
is
have the
x-axis?
random variable values of the random variable -1, minus 0.5, minus I mean 0.7, 1.5, and 3 are the random variables.
Ah, very good. In other words, what I say is the minimum value the random variable takes is -1. Maximum value the random variable takes is 3. How do I know that? At x equal to 3, the value of the distribution function has become 1. What is the second property of the distribution functions? Fx of infinity equal to 1. What is that infinity in the argument? The infinity in the argument says the inclusion of highest possible value, inclusion of all possible values of x. Fx of infinity is probability of x taking a value of -1 plus probability of x taking a value of minus 0.5. I'm referring to the same figure. Probability of x taking a value of 0 plus probability of x taking a value of 0.7 plus the probability of x taking a value of 1.5, probability of x taking a value of 3. Is it clear, please? That is what is meant by the value of the distribution function at x equal to infinity. Then what is the meaning of x taking a value of minus infinity?
minus
By
1.
minus infinity, what we mean is a value less than the least value taken by the random variable. So in this example, the least value taken by the random variable is minus 1. Consider a value slightly lesser than that, maybe minus 1.1, minus 2. Okay. So the value of the distribution function at x equal to minus 2 is 0. That is the meaning of first property. So like that, please correlate the properties. Any other property which you would like to analyze using this figure?
Difference of probability of zero point 0.7 random variable is obtained from difference from minus zero point 0.5 and 0.7.
Oh, okay. Yes, correct. Because x2 is on higher side. Okay, correct. So like that, if you are given a curve, you can infer whether it is the distribution function of a random variable or not. Every property can be seen. What is the maximum value of this function? 1. So that is the property. What is the minimum value of this function? 0. Is there any negative value for this distribution function? No. As x increases, okay, as x increases towards right, the value of distribution function either increases or remains same, but it will never decrease. Can you notice that? As you include more and more values for small x, the distribution function value keeps growing, or it remains there only at least. It will never fall down. That is another important observation. So from the figure, the random variable can take values from minus 1 to 3. Okay. Okay. Once the random variable fx of x distribution function is plotted, how do I plot the density function? By taking the derivative of that distribution function. By derivative, what I mean, you need to consider the slopes associated with the distribution function. When you take the derivative of this distribution function, whenever there is discontinuity, you will get an impulse. Okay. So where do we expect impulses? At x equal to minus 1, x equal to minus 0.5, x equal to 0.7. Now you see the density function. Okay. At x equal to minus 1, there is discontinuity. At x equal to minus 0.5, at x equal to 1. Okay. There is a, see, at 1 there is no discontinuity, but lower side of 1 it is 0.7, there is discontinuity. At 1.5 there is discontinuity. Okay. Just you make sure that you correlate these two graphs. Okay. Then it becomes clear. Now when you look at the density function, what is the notation for a density function, please? So I will expand to see only density function. Fx of x, lower case of f, the subscript is capital X, which refers to random variable. Argument small x, it represents values. It is a train of impulses. When I have train of impulses, how can I show density function? It is sigma impulse train delta of x minus xi. What is the strength of each impulse? The value of the probability corresponding to that value of x. So it is written mathematically like this. Distribution function like this. Okay, density function, let me write down. I think in the textbook somewhere far away that is given. Okay. The density function is the derivative of the distribution function. So I am taking the derivative of this last expression. Summation exists. In this, p of xi is a constant value. So I need not subject that to derivative. Only impulse, unit step function. When I take derivative of unit step function, I get unit impulse function. Is it fine? So what is the inference we make, or what is the interpretation we give? The density function is a train of impulses. Each impulse is weighted by this p of xi. Okay. Now the question is, this type of density function is for the given uh, distribution function. Because the distribution function has got staircase property, the density function has become train of impulses. Okay. From this figure, can we comment on the value taken by the random variable x between 0.7 and just greater than 0.7 and just below 1.5? My question is clear. I wanted to know whether the random variable x is taking any value between 0.7 plus to 1.5 minus. Please respond. The question is not clear. Please ask me. Amrita.
Yes, sir.
Question is clear? Okay,
Can
I
you
will
repeat
repeat.
that?
Please. Question is, from this distribution function, can I
Okay.
infer that the random variable takes values between 0.7 plus to 1.5 minus?
Sorry. Um.
Okay. You can
Okay.
say yes or no. Okay, I will
Uh,
say yes. The random
yeah.
variable is taking values between 0.7 to slightly higher side of 0.7, slightly lower side of 1.5. But
Yes,
I
sir.
say the probability of occurrence of that value is 0. That means the values are occurring with 0 probability. Okay, that
Yes.
is my answer. If I say no value is happening between 0.7 plus to 1.7 superscript minus, that is also right, right?
Yes, sir.
So random variable is taking values specifically minus 1, minus 0.5, 0.7, 1.5, and 3. Such a random variable which takes values such as discrete values is referred as discrete random variable. So this figure which is displayed is an example for distribution function of discrete random variable. Is it clear? Because random variable is taking discrete values. Between minus 1 to minus 0.5, no value exists.
Yes, sir.
Any question, please?
No, sir.
Okay, thank you. One is someone
Sir,
is responding.
actually, you are saying the statement and you are contradicting itself now,
Yeah,
sir.
yes. See, yes, exactly. Very good point to be observed, right? I am saying event is happening with 0 probability. The event is not happening. Both are same. Immediate answer is yes, event is happening, I said. Then after little thought, I conclude that no event should have happened. So I am correcting my statement. The event is happening is earlier statement followed by with zero probability. What is not happening? Yes, I am contradicting. Only thing is, see, sometimes we start speaking, no? Yes, I have done. I think there is some problem. That means I have not done, right? Any other question, please? I hope I could answer the question raised by. Did I answer, please? There is one more example. Yes. This is another example for distribution function. So from this, what is clear, please? I want you to speak out so that Madhu is on the online, please. Madhu, then
Yes, sir.
if you are online, please respond. Vaibhav,
Yes, sir.
Madhu
Yes,
is
sir.
there online? Okay.
Yes, sir.
Please. From this figure, what inferences can we make?
Well, and there is no value. It is taken in between 0 plus and 12 minus.
What is 12? Okay. 0 to?
But in between 12, it is not taken.
Any other observation?
Continuous random variable.
Continuous. Very good.
Sir, between 0 to 12, every value is a possible event.
Very good. That is the case of continuous random variable. If you ask me, what is the probability of random variable x taking a value of 6? From the figure, I will draw a line parallel to y-axis like this. Okay, where that vertical line intersects the curve, I will draw a line horizontal to x-axis. I will land on to the y-axis and I will read that value. Is it fine? If you ask me, what is the probability of x taking a value of 6.1? I have to identify a value of 6.1 along x-axis. I have to move parallel to y-axis up, then move left-hand side parallel to x-axis and see what value happens on y-axis. So it is the case of continuous random variable. Another question is it a function to be called as distribution function? What are the checks? Maximum value should be 1 and minimum value should be 0. It should be positive for all values of x. Then if I consider two values for random variable x1, x2, when x2 is on higher side, the value corresponding to x2 for distribution function must be on higher side. All properties are being satisfied by this curve. Yes or no? So that is how we need to check whether the given expression represents a valid distribution function or not. What is the corresponding density function, please? Take the derivative. Since this curve has got constant slope between 0 and 12, when you take derivative, you get a rectangular pulse. So how do we get the slope? Spread on y-axis, you notice. Spread on x-axis, you notice. This is the corresponding density function. From this density function, what inferences can we make? The random variable x is taking values from 0 to 12. Since density function has got constant amplitude, what we say? The distribution function is a linear function of x. These inferences we can make. Is it fine? Then the next question is, what are the properties of density function? I have defined density function, but I have not defined the properties. Okay, let me see. The next topic is that only. Yes. This is how density function is defined, and the properties, they are listed. List the properties of density function. That is another important question. What the first property says? The first property says that density function is greater than or equal to 0. It is always positive value. And area under the density function is 1. How do we get area under the density function? Write down mathematical expression for the density function. Integrate with reference to x. That should be 1. In the example we discussed in the previous case, that is, the density function is in the form of a rectangular pulse. The area under that is simply height into width. So what is the height of this density function?
1 by 12.
1 by 12. What is the width, please? 12 units.
12.
So area is height into width. So I got 1. So this has satisfied the second property of the density function. What is the first property? Density function should have a value greater than or equal to 0. Okay. So the density function between 0 and 12 is 1 by 12. Beyond that range, its value is 0. It is never negative. Please notice that. It can never become negative because the distribution function either will remain flat, constant, or keep growing. It will never decrease, right? Distribution function will never decrease. That's right. Density function will never become negative. Let us see the third property of the density function, that is, to get the value of the distribution function at a specific value of x, that is what right hand side, I need to integrate the density function from minus infinity to that particular value of x. Okay. Normally when I take density function derivative, distribution function derivative is density function. If I take integral of density function, that should lead to distribution function. Okay, whenever I integrate density function, see the upper limit. The upper limit is x. Okay, what is the argument for the density function in the integrand? Density function fx of zeta, right? So independent variable is different from x. When you integrate, that independent variable disappears and it will be replaced by the limits. The limits are indicated as x and infinity, minus infinity. Is it fine, please? If you are good at integration and differentiation, then computing density function, computing distribution function becomes very simple. Any comment, please? Only thing is revise your knowledge about integration and differentiation. That's all. This is xi, right? Okay. Fourth property is the value of the area under the density function. I am referring to right hand side part. The area under the distribution density function between the limits x1 to x2 is nothing but the probability of the random variable taking a value greater than x1 and less than or equal to x2. Is it appreciated? In fourth property, replace x1 by minus infinity and x2 by small x. Is it okay? in fourth property, how do I get property 3 from fourth property? In the fourth property, let me replace x1 by minus infinity, x2 by small x. Then I will get third property. Is it okay? Okay, come to the left hand side of property 3 and property 4. Left hand side of equality sign in property 3 and property 4. In property 3, it is the distribution function value at a specific value of x. In property 4, it is probability of capital X lying between two limits, two bounding values. Okay. How can I write fourth property? It is nothing but property 4, left hand side, it is nothing but fx of x2 minus fx of x1. I hope the difference between third and fourth properties are clear. Any questions till now, please? Please try to work out the problems under each concept, right? This is followed by example 2.31, 2.32 also. Please work out them. Any questions still now? Okay. Sarath Chandra is online, please. I am not able to see the name. Yes. See, if there are no questions from what I have explained so far, okay, let me refer to the questions raised by our friend. Okay, this is, yes. Sarath, this is Papalis book, okay? About which concepts do you have a question? You mean this chapter only? Okay. See, in this chapter, you see worked out examples. This is one worked out example, right? Yes. What is this? A resistor is commonly viewed as a two-terminal device whose voltage is proportional to the current. Okay, that is the formula. What he is trying to explain? Probably he wanted to bring out the concept of a random probability concept, right? Can you frame a question out of this equation? Can you please frame a question out of this equation 1.2? See, and as just one line before that, as an illustration we discussed in example 1.1, the interpretation of the meaning of resistance in circuit theory. Okay? So nothing can be formulated as a problem. So don't take up such things. Let us see next example. Where is 1.2? Yes. Example 1 point. We roll 2 dice. Okay. And we want to find the probability P that the sum of the numbers that show up equals 7. Okay. This is a problem to be worked out by you. So how do you go about this? Okay, let me show. Okay. While you are writing assignment example 1.2, let me briefly explain and close the session. Okay. So sample space S equal to 2 dice, right? So, how do you take, if you take it as a combined experiment, you should show the elements like this 1 comma 6, then 2 comma 1, and so on 2 comma 6. Like this, you have to go 6 comma 1. Is it clear? Then you should say number of elements in sample space equal to 36. The sum of the things that show up is 7. So what are the possible combinations? On first die 6, second die 1. This is one combination. First die 5, second die. Third die, first die, second die. Like that, you have to consider the possibilities, right? 3, 4, 2, 5, then 1, 6. So how many such combinations? 6. So number of elements is 6. Number of possible combinations is 6. So probability is 6 by 30. Like this, you have to show. Don't write all the theory. Okay. I hope I am 6 by 36. Work out the problem as you understand, as you understood. Okay. The idea of asking you to work out all worked out examples is for your mid examination, for your end examination, you should be able to refer to your notes quickly. Okay. So whatever you do, you work out the problem as you understand. That is very important. My intention is not to force you to reproduce all the steps, but as you work out, see, this is how I understood the problem. So this is how my working out is. If you understand the problem in a different way, put down the steps accordingly. Don't write theory as given in the textbook. Okay. For every problem, please follow that. This is 1.3. Here also circle of radius is. Here so much of explanation is given. Don't write all the explanation. Okay. And at the same time, don't write p equal to pi r square by 4 by pi r square equal to 1 by 4. You should tell the reason why the numerator is pi r square by 4, why the denominator is pi r square. For that, you should write the corresponding explanation. Sarath, I hope I am clear. Any other question, please?
Sir, so we should write how we solved that question. That's it.
Yes, yes. Once I go through the solution offered by you, I should understand your thinking. Your thinking comes only when you explain the reasons behind each step. Okay? When you reproduce the text from the book, it will not reflect your thinking. When you try to present your thinking, you will never reproduce what is given in the textbook. That is the logic. Any other questions, please? If there are no questions, let me close the session for today. Thank you so much for staying with me. So I am closing this session for today.
Excuse me,
Thank
sir.
you. Please.
Sir, for a discrete random variable at points where there is a discontinuity, how do we find the derivative there? In
At
finding
points, yes.
in
Where
finding density.
Yes. Correct. Good question. So at points where there is discontinuity, x1, x2, it is a practical limitation, right? That's why we will take the help of the impulse function. That is how the concept of impulse function has come. Wherever there is discontinuity, we replace that discontinuity by impulse function. Is it okay? Did I answer your question, please?
Yes, sir. What will the value of the function be?
Yes.
Impulse.
The value of that density function is, what is this step height? So this step height which I am showing on the screen is p of x1, right? That p of x1 is the strength of this impulse. At x equal to x2, the discontinuity over here is p of x2. Are you able to notice, please? So this
Yes, sir.
discontinuity is indicated by this impulse strength, that is p of x2. Is it clear? Previously also I have indicated, that is what I remember. Anyway, it is good that You ask, put a question. Any other thing to be clarified, please?
No doubt, sir.
Oh, thank you. So, if there are no questions, I will be closing the session for today. Okay. Thank you for staying with me.
Thank you, sir.
Thank you. Thank you. Thank you. Thanks to everyone for staying patiently.